go ahead and get started today. I'm Tanya Tabuki-Herrera. Thank you for joining us. This is the 90% design review. Hopefully everybody's had a chance to flip through the drawings and technical specifications and calculations that were made available online. I'll go ahead and let the team introduce themselves, starting with John.
Get myself unmuted first, right? Hey, so yeah, I'm John Berge. I'm a civil engineer, project manager for McMillan Jacobs, kind of heading up the design aspects of putting together these plans and specs and getting this ready for construction.
Hi, I'm Dave Thomas with eCorp Consulting. I'm a senior fisheries biologist and project manager, and our company is leading the permitting process for the project.
Hi, I'm Chris Stabenfeld. I'm with eCorp and I'm the project director for the project.
Hi, I'm Courtney Owen, senior biologist with eCorp, helping with permitting.
All right, great. So again, thank you for joining us. The intent here is to have John walk through the documents and then also be able to answer any questions that you may have. So with that, John, I'll go ahead and turn it over to you and you can start sharing your screen.
All right, I'll get my screen up here and see if we get the right one. We got the one where we are, there we go. Like now we're looking at the plan set now, right?
We are. Oh, and one more thing, so this is meant to be an organic type meeting. So if you have a question or comment, feel free to raise your hand and I'll unmute you so that you can engage with us instead of waiting until the end. And in order to do that, there's the raise your hand function at the bottom, or from your phone, I believe it's *9. All right, John,
excellent.
Sorry, go ahead.
No, that's great. Yeah, so please do jump in. And if a hand goes up that I don't see Tanya, because I probably won't be looking at that screen, just jump in and interrupt me. It will be great. So yeah, we've moved forward toward the 90%. I think probably the folks that are on the phone have been kind of walking along this road with us, and probably not going to be a whole lot of surprises of what we see and go through here. But again, I'm happy to share kind of where we're at on the design pieces, some of the pieces that we're still developing and where that's taking us, maybe some of the conversations we've had internally and with some of the agencies, and just kind of walk you through what we've got. So yeah, I think you guys are familiar with the project, Hemphill Diversion project. There's an existing diversion dam that they use to get water out into the Hemphill Canal, which flows off this way, off of Auburn Ravine, which is heading downstream this direction. With a few sheets here, this is just our title page sheet or kind of the table of contents where we show the different sheets included. Some of the sheets that we're still developing and pulling together, some of these specific mechanical details and sections and details of the different mechanical pieces. So that's a piece that's still pulling together. A lot of abbreviations and standard symbols. Again, this is kind of the existing conditions. There's this existing concrete diversion structure that's kind of a stand-up structure, a stop log structure where they put in boards to stop up the water, to back up water here in Auburn Ravine that allows NID to divert water out Hemphill Canal. So I guess we'll probably get to it in a couple of shots here. But yeah, so this is just kind of the overall, shows the survey points, helps the contractor get oriented. This here is our general site plan, contractor staging. Just kind of shows different areas of kind of the overall what's going to be happening. So this area here to the south will be a contractor staging area. There will be a new southern access road that NID will be putting in, or the contractor will be putting in, that will end up being a permanent access for NID to have access to the facilities they're building. So it kind of curves around to stay within the project boundaries to avoid some of the elderberries and other neat things like that, trying to minimize the number of trees that we affect. There's a lot of trees growing throughout this whole area. So we really tried to go through and find the best alignment we could that would do the least long-term damage to the area.
John, we have a question from
Yeah.
Jim. Jim, you should be able to unmute yourself and talk now.
Yeah, hey, Jim Hoffler here. Thank you very much for this presentation. At the top of this diagram, going up towards Virginia Town Road, there's a little thin line that indicates an electrical line underground.
Correct.
Is that going to be actually used for the operation of the conical screen?
Correct. Yep.
How is
So-
the power? Oh, go ahead.
Yeah, so we'll get that into a bit, but go ahead and ask your question.
I was just going to say, how's the power going to get across the creek?
Yep. So we'll drop it down off of the overhead lines on Virginia Town. We'll run an underground line down that north access road that's existing. And it'll just cross the creek underneath. So after the existing facility's been removed, and probably, they've got this whole area dewatered before they start putting in, it might be after the sheet pile, maybe before, but somewhere in there, they'll bury that, that underground line underneath the ravine. And so it'll be buried, probably just downstream of the sheet pile. So it'll be protected by that, be buried down underneath all of the rock that'll go in for this roughened channel. And
Right,
it'll
and
pop
it'll
up over
be-
here.
Just to clarify, so it'll be a casing, and then in that casing, we'll have conduit for the electrical line.
Yep. There you go.
Thank you very much.
So yeah, this just kind of identifies the temporary areas of impact, permanent areas of impact. So yeah, that's that impact map. This one here is just kind of showing the hydraulic grade lines to give folks an idea of just what's going on with these 5% and 95% are kind of the upper and lower fish passage limits that we want to hit. And so actually this drawing here is still being updated as we finish off our hydraulic modeling to be able to show that. Then this just kind of shows the different discharges. Again, this 5% exceedance, 95% exceedance. And then we've got this, as we've talked about before, if you've been following along, this really large 100-year FEMA flow of 15,000 CFS, which puts that line way up high on the profile. And then this one here just kind of gives a kind of really simple profile of what the cone, the pipe, the outlet control box, and back into the canal will look like. Again, you have these same water surface elevations here, 100-year event up top. And I'm just showing kind of where the 6 CFS or where 18 CFS, what that would look like in Hemphill Canal. And we'll kind of drill into this profile a little bit later. We have a little more detail. Here's just some of the criteria for the fish screen that we're putting in is kind of a low flow of about 3 CFS. Normal flow right now, Hemphill Canal carries about 6 to 8 CFS, but this system will be designed for up to 18 CFS. It's all got this max approach velocity of the 0.33 feet per second, which is the CDFW criteria and NIMS criteria for this type of screen. This one's just, it's the pipe schedule, and we only have like 1 pipe, so it's a really boring pipe schedule. Some of our projects, we fill up that sheet. This is kind of our demolition plan where we show the different parts that the demolition will be happening. So we'll be demolishing this existing structure here. There will be some trees in the ravine that will be removed as part of that, as part of putting in that roughened channel. There's an existing head gate here that will be demolished. Again, there'll be a tree there that'll be removed. There will be this existing canal gauge that'll be demolished here. And these are some of the pictures of some of those items of what they look like. This is just trying to help the contractor know there's rock and grouted riprap. and structure here that he's got to take care of. Here you can see that stand-up diversion dam. This is what that existing headgate facility looks like, and then there's a pipe under the ground that the contractor will need to remove. This is the existing gauge that'll be removed. Here's some of our standard erosion sediment control measures that'll be put in place that give some direction to the contractor of what needs to go in there and what it needs to look like. One thing that I'll just draw attention to so no one gets too excited. This I asked for the construction fencing detail, and my CAD staff put in this construction fencing detail, which is an 8-foot tall chain link fence with barbed wire on top. But that's not the construction fencing we're going to be doing. We'll be doing something that'll, it's just the high vis orange, 3-foot tall plastic fence that'll just kind of highlight where the construction area is for public safety, but it won't be this secured facility, prison looking thing. We don't want that out there. This sheet here is our erosion sediment control plan, where we kind of try to lay out for the contractor where all these pieces will go. And so you'll have this access road, you'll have this construction fence that'll be coming around it. There'll be construction fence around much of this. There will be silt fences that are going in there as well. There's silt fence up there. So in some of the areas we'll have silt fence as well. There it is. Kind of on the between the construction and the ravine will be silt fences to protect those areas. And then just a lot of words to let the contractor know what's expected of the erosion and sediment control, and the requirement for them to submit plans to us to approve of what that's going to look like, and kind of make sure they're doing that correctly.
We got a question from Steve. Steve, you can go ahead and unmute yourself.
Hi, thanks. Steve Hubbard. Question, you have the new access road from the southern approach. Does this mean that NID is going to abandon that easement and access road on the north side of the project?
No, we're not intending to do that at this point. We'll have both the north and south access.
Thanks.
Yeah, they'll have that underground wire, or that that power line that's running underneath there. And then also just for NID carries kind of an ongoing maintenance requirement or commitment with this roughened channel. And so they really do, since they won't have that walkway over the ravine anymore, it'll be really helpful for the district to have access to both the north and south side. If some of these rocks move, or if there's some additional work that needs done in here, it would be really helpful to have that access on both sides. All right, some general civil notes here. Nothing super exciting in that. This is just a key plan showing the kind of the two different aspects, two different parts of the project. This one here is a dewatering plan. So this is where we kind of highlight in just very broad brush strokes of how dewatering could happen. And in the end, dewatering is something the contractor needs to put together a plan, submit that to us for approval to make sure it works. This is just intended as something to show them how it might work. So it'll be like a cofferdam on the upstream side, cofferdam on the downstream side. There'll be a pipe or a channel that will channel the Auburn ravine water, likely around this side would make the most sense to stay out of the way of construction. There will also be a pipe with a screen on the end of it here that will be bringing water into Hemphill Canal. And there will be a little cofferdam here to allow for the construction of the facilities here in Hemphill Canal.
We have another question,
Yep.
John, from Jim. Jim, you can go ahead and unmute yourself.
Yeah, I had a question about sheet note D, as in David, talks
On
about
this sheet,
on that sheet note D
Yep.
talks about a flow of 65 cubic feet per second would need to
Yeah.
go through that pipe to carry the Auburn Ravine flow.
Yep.
I'm concerned about that because we have seen during irrigation season, during the last 9 years in particular, I went back, checked my notes from 2013 and 14, we've seen flows in the 80, 90, even over 100 cubic feet per second at the Lincoln gauging station, which is a good indicator of what came over Hemphill Dam because nothing really goes in or out
Yeah,
of
so
Auburn Ravine downstream.
when I looked at the data that I had from what had gone over the Lincoln gauging station over the last 9 years, and I wasn't looking at the irrigation season because really we're concerned here about the in-water work season. So just from June 15th to October 15th, that this was kind of where it peaked. So there definitely weren't any
Yeah.
100 CFS flows in that range. So I don't know
Well-
if maybe that 100 was like pre-June 15th, maybe?
Well, I had a reading of 80 CFS in July of 2014. And I'll
Interesting.
tell you, just so you know where this data came from, this is my eyes looking at the yardstick gauge at the Lincoln gauging station.
Okay,
I
yeah.
used to only live a half mile from there. We would walk down there frequently and I would just take note of what it said on the yardstick gauge. But I have another idea for you.
Yeah,
I think you ought to talk to Placer County Water Agency about it because theoretically, the water that goes past Hemphill on downstream is PCWA water during irrigation season
mhm,
because NID's last customer is off of the Hemphill Canal somewhere, right? They don't have any customers at present. They did years ago, but in the last
Right.
5 or 6 years, didn't have any customers downstream from Hemphill. So you might ask PCWA what their plans are for this year during the period of time where you think you'll be working in the creek. We might actually have kind of a perverse benefit here because with the drought, they might not have a lot of water to deliver. So that might be, that's
yeah.
perfectly fine. But
There you
yeah.
go. Yeah, that's a good thought. And yeah, kind of, the intention here is to give the contractor an idea of what water he might be dealing with. But yeah, so if there's any way that we can, the more we can educate the contractor, the better he's prepared to deal with this and the fewer potential issues we have. So yeah, that's a good idea and be a good coordination to make as we move
Okay.
forward.
Yeah, you could talk
Oh,
you
go
could
ahead,
talk-
James.
yeah, you could talk to Placer County Water Agency, Ben Ransom, or I'm forgetting the man's
Yeah.
first name, but his last name is a perfect name for a water guy, Passmore, Passmore, over at NID.
Yeah.
And they could tell you, I'm sorry, over at PCWA, and they could maybe give you an idea what they think might be their ability to deliver and their actually demand west of Lincoln coming in the
Yep.
coming season.
Excellent. That's good.
Okay.
Thank you.
I don't think, just one other thing on, our intention in, I'm pretty sure I've got it in the notes, I'm not positive, but to have these be gravity feed systems. So it's likely that this cofferdam upstream will end up backing up water very similar to how it used to back up with the or how it's been backing up with the existing diversion structure, to date, so that they can get water both into Hemphill Canal and actually get measured by the gauge down here, the existing gauge, but also so they can get water kind of back up over the bank and into Auburn Ravine again. They'll have to do some cutting and putting that in the ground there, but that's the intention. Next sheet is, so just kind of zooming in on this roughen channel. So this is the roughen channel that we've been seeing for a while. We'll have a sheet pile that will go basically bank to bank at the front end of it, which will really kind of define that, define and hold, stabilize that beginning of the roughen channel. There will be some rock upstream of that that's kind of protecting that sheet pile, trying to help the hydraulics of the water flowing over. But also we'll see here in a little a detail just what this looks like with the rocks coming up over the sheet pile to try to protect fish a little bit better. And then there'll be a low flow channel. One of the changes that I think we probably made since 50% is this used to be just a triangular low flow channel, but now it's a triangular in the bottom and then it steps up to a trapezoidal before going off into the sides. And so we'll kind of jump ahead and maybe we'll just do that now. Jump ahead and see that. Oh, there's those details. So here's this kind of a typical section. So we'll have a little triangular channel in the very bottom of the low flow, and then it'll step up into kind of a trapezoidal. This trapezoidal will carry, in the range of 40 to 50 CFS, something like that. And so then once the water is up above that, it'll start coming out onto these sides where there'll be at the very, well, we'll get to that in a second. So there'll be kind of slopes on the sides of these guys. This is the sheet pile cutoff wall. So the intention is to have the sheet pile driven in, but then to have kind of a rock that's in this engineered stream bed material coming up to, coming over and on down, just so that we don't have metal sticking out of the ground there is kind of the intention. All righty, we're gonna step back here. And then there will be kind of a transition zone here at the very end is kind of what this area right here is just transitioning back to the natural stream. This will just be, rock with D50 of 2 foot or something like that. It'll fill in this area and really gets just makes that transition. Trying to think of other things there. This is, so kind of a profile of what this could look like is you'd have this material up on the upstream side of the sheet pile. Like I said, it'll kind of come up over the top. We'll just have this spread of large rocks. So, before maybe I think I had a plan that showed big rocks in specific places. I think we're just going to go with just dispersing these group A and B rocks throughout the channel. Those group A and B rocks are, I think they're ranging from, 3.5 feet down to 2 foot or something like that, if I remember right. We can look in the specs and see just exactly what those were. But these are kind of the bigger rocks that'll really stabilize the system, but also provide that refuge back behind them. So probably I should have these in the detail sticking up a little bit more. But these will all be buried, at least 2/3 of these rocks will be kind of in the ground or, buried in the rest of the material. This
We have a
ESM, questions are coming. Yep.
Sorry. We have
Jump
a
on
couple
me.
questions. Steve Hubbard, why don't you go ahead, please?
Okay, hey, thanks. Hey, in looking at that diagram there at the head of it, it looks like it could form almost like a small dam and impound some water upstream of it. So I'm wondering, will that happen? Will it impound water? And if it does, how far upstream is that pool going to extend?
Yeah, it likely will impound some water, just the way the existing contours of Hemphill Canal or of Auburn Ravine exist. There's kind of this low area here where you can see elevation 195. That existing concrete sill was at like 197, and that's really kind of what we're using as the low point for us. So there will be an area here that will collect, that will pond water. So maybe we can see it on this one. So if we go up from 195, 96, 97 is this contour that my hand's sitting on right here. So that's kind of what, that would be probably the extent of that pond is, unless things change up here, you're going to have a pond here where there's a natural low spot. But it's going to be pretty low before water starts tipping over. So probably more realistically, it'll be at 198, I guess, because we'll have 1 foot of flow. So 5, 6, 7. So it'll be up to this one over here then. Would be the, so yeah, kind of that area. Does that kind of see what I'm saying there, Steve?
Yeah, that's not that big of an impoundment actually.
Right, yeah, so it's going to be a very small, it's going to be a place where the water is going to be flowing slower than it is in other places as it kind of gets ready to come out there. But that's we needed to back it up a little bit to be able to get any water out, but not very much.
Thanks.
Yep. And then James, did you have something?
Be able to unmute yourself now, Jim.
Got it. So on the far downstream end of that diagram, it shows riprap transition to natural stream bed with riprap.
Yeah,
Now, what you have drawn there is not exactly what I would call riprap. It's more like boulders. Riprap, more classically, is very jagged. I mean, the more jagged, the better.
yeah,
So I'm guessing you probably don't really mean to put jagged rock in the stream bed. Is that true?
that is correct. That should not be riprap. It'll just be, it'll be the same ESM material that they use in this, but we'll just be kind of, you know, selecting out the larger rocks there.
Okay,
Is what
thank
we're
you.
trying to do there. And just another thing, I don't know if you guys, so this this dotted line here is the existing stream bed. And if I say this is transitioning to natural stream bed, you can see right here isn't right there. And so kind of that's a function of just where we're trying to land this low flow channel toward the middle of the channel of the Auburn Ravine. The thaw wag, which is the low, kind of the low point of the stream, is actually over here. And so at one point we were kind of following the thaw wag and sending this low flow channel that way, but then it just is pointed right at that bank. So we're going to try to kind of realign the stream a little bit. There's kind of a sandbar out here, and that's, I think, probably what we're seeing in this high spot right here. So I think it's going to be a little bit of a field fit to make this work and to fit in there and look right. But that's kind of why you see that that difference there. Okay, I think that's this table over here is just showing these different points for the contractor to build. It will have elevations to it as well. The CAD just couldn't get it to work right when we were putting this together. So each of these points will have an elevation because that's how the contractor knows just where to put this this low flow channel in there. These are some of the sections of what this would look like. So station 100 is where we start with the sheet pile. The sheet pile will go down about 15 feet. We're just finalizing that to make sure we know the right spot to put it down to. It's not, you know, necessarily a super structural piece, so we're not having to get down into like fractured rock or anything like that. It's really functioning as something to help stabilize the rock behind it, but also to just help force the water to come to the surface. So if there is any water that's flowing, you know, through the sediments in the bottom of the ravine, they're going to need to come up to the top. So then we'll have this kind of this stepped section that I showed you before. The other thing to note is at the sheet pile, this side slope is 0. So once you get out of this trapezoidal area, it's just going to be flat going over to the side. And the reasoning is, if you can see this dotted line that goes behind, it's kind of right through there. It's a little hard to see. So we're actually raising on the sides, we're raising that the elevation of that existing concrete structure just a little bit in order to focus that flow so that when there is low flows, we can have it for the fish to be able to come upstream. We need to keep it flat because one of the other things we've been working on is trying to make sure that we can put together a no-rise certificate with FEMA, just saying that these changes that we're making in this structure are not creating a rise in the flood, in the 100-year flood. And so to do that, we really had to keep this flat here at the top, just to allow the water to pass over. And then what it does is as you step from like station 100 to station 125, you'll see it starts sloping. So it'll transition from station 100 to station 150 and go from a side slope of 0 to a side slope of 0.05. So it'll have some side slope. It's not a whole lot, but it'll be enough to where the water is just not getting lost, where it is kind of focusing it a little bit. So that's kind of the thought process there. I'm showing these rocks on the side. Again, these are just going to be kind of bank rocks. They're going to be the bigger of the ESM sort of rocks. We're going to plant some live stakes and willows here on the sides. I'm thinking we'll have like one on each side and maybe spaced out every 15 feet or something like that, to try to get some plant growth to come back on those banks. As we go downstream, you can kind of see we're here at station 150. We're going to be filling in underneath where that existing, that steep section coming off of the existing structure. There's a pool down there that will need to be filled in. I don't think there's a whole lot else exciting on these sections. I guess one thing maybe I didn't talk about back here, I have so many of these conversations I forget, is I think a change from our 50% is now from the station 100 where it starts, we go down to station 260. So that the total length is 160 feet to get from the top to the bottom of our structure at this point. And then the slope, which it doesn't look like I showed here, but because of some of the changes we made, our slope is now, it's like 2.8%, I think is what it is. So we were able to drop that down, or yeah, we're able to lower the slope because before I think we had a 4% slope. So we're able to lower the slope and kind of shorten the ramp a little bit as we kind of move through the design process, which were good things for everybody, I believe. Talked about a couple of these details. This other one here just kind of highlights how this ESM goes in. Kind of the idea is you place these big rocks first, and then you bring in a foot at a time, this smaller stuff, and you do this flooding or jetting as a way to get the sediments to really sink down in. And when you've got big rocks, like how do you get sediment down in here? How do you get rocks down, material here? And so that flooding and jetting is a process that contractors use to really use water to get that material down in there. And then the idea is that as they do that and step up on 1 foot lifts, so there'll be, I think our total depth is 3.7 feet. So there'll actually be 3 1 foot lifts and then a 0.75 lift on top. That at each one of those, they check it to make sure that it's sealing up and it's keeping, and water's flowing on the surface or ponding on the surface. And that's really what we're looking for, to keep that water up on top where the fish can take benefit of it and really create that natural system. Here's where we talk about, no more than 1/3 of the rock protruding. And this will really, and as we've had some conversations about this whole building a roughened rock channel like this with this ESM, really there's an art to it. And it's not just, backing up the dump truck and dumping rock out into the stream and see what happens. There's a real art to it and a method of laying it out. And so, we'll be working with the NID staff to make sure they understand those things and they're able to help direct the contractor. And we're looking for contractors that are qualified and have experience in this type of work to really help make this be a workable system moving forward. All right, so this is the kind of looking now at the cone screen and then into this control box. We'll look at some details later, but some of the things that have changed here is, I guess I don't remember, we've got a 10-foot diameter cone screen is what we're doing, which gives us that flexibility to go from the really low flow of 3 CFS up to 18 CFS and stay within criteria. It'll be like this concrete alcove that we'll set up here. It's going to have a catwalk out here that'll go over this front part. And there's going to be stop logs on the front face of it. And kind of the intention there is for the district to be able to dewater the cone screen if they to do maintenance, or if they just want to keep it dry during the off season, they have that option to do that. Or if they need to protect it, if there's material coming down or bed load coming in, there's options they'll have with those stop logs to be able to just make it a usable system. The water will flow out the bottom of the cone screen, and there's a 3-foot diameter pipe here that'll come over to this control box, and the water will flow into the control box. We'll look at a detail of this a little bit, and then it'll flow out through both a flow meter and a slide gate as it heads out into the canal. Part of the canal will need to be regraded, as we've talked about before. And it looks like we go from station 100 basically up to station 323. So yeah, there is about 225 feet or so that we're we're going to be regrading there. And this little bump right here is where you see that existing flow measurement ramp that the district has in place.
Tom,
Yep, question.
we have a question from Jim. Jim, you can go ahead and unmute yourself.
Yeah, could you go back to that view of the alcove?
Yeah.
So I noticed the indication of the stop logs and how they're going to be used. On another page, it mentioned the stop logs would be made out of aluminum.
Yep.
And that started worrying me because there's also a lot of iron involved there. And if you had iron and aluminum and water, electrolysis becomes a problem.
Mm-hmm.
Now, maybe that's not such a big deal because you were saying that the stop logs might just be put in for short periods of time. But what are your thoughts on that electrolysis question?
I'm definitely not an expert in that, but I think that the steel that we will be putting in will be stainless steel. So I don't know if that helps that situation.
I'd have to go to my electrolysis chart and see what nickel versus aluminum does. It might actually
Exactly.
be worse. I'm not sure.
I'll touch base with our, structural and mechanical engineers. I know we do this type of a system a lot in underwater situations.
Okay.
And so I know that this, they totally get that this is where the whole point of this project is trying to help aquatic species have a good life here in Auburn Ravine. And so, yeah, I'll double check on that and make sure we don't have an electrolysis issue.
Yeah, because the issue with electrolysis is that the aluminum and the iron and a lot of other dissimilar metals will actually generate electric current basically in between two, and either one or the other will be corroded as a result of the electrolysis. So I forget right now where the aluminum goes away or the iron goes away, but one of them is sacrificed.
Yeah,
and would tend to weaken the structure over time.
yeah.
Maybe there's an option just to use plain old wood.
Yeah, there could be. These spans are pretty long. So that's one of the reasons that we've gone with stuff like that. And also we've got, I think you probably saw there's, is it a neoprene on the bottom of it that we try to use to really seal it off. And stop logs can be hard to seal, but
yeah, exactly.
there's ways around that.
So another question on this, how is sediment going to be cleaned out?
Yeah, so kind of what we've done is, let me answer that in a couple ways. One of our versions of this had a sill right here on the leading edge of it to try to keep sediment out. As we looked more at the existing ground, I'm just not sure that it's needed. This is one thing where if the district is seeing a lot of bed load come in and creating a sediment problem, then they could very easily come in and put in like one of their 6-inch stop logs or something in part of that and try to stop that. So that's one thing they can do to try to limit that. Sediment will collect there. I'm sure that there will be some. We've also, we're trying to, just encourage water to kind of flow through as well as much as it can. But then if sediment does collect, the answer is we've got a ladder here that at the end of the season or before they start for the irrigation season, the district can climb in there and shovel out sediment is kind of what that'll look like.
Thank you.
Yeah, at one point we were looking at like a sediment sluice way that would be able to sluice the sediment out, but it became a losing battle with the agencies that, it would just, since it would be a pipe and since fish could get into the pipe, it would need to meet all the bypass criteria. And that was just going to become really difficult. And this is just an easier, cleaner way to take care of it, I think. Okay, I see another question.
Yeah,
Hi.
one more.
I got a quick one for you. This is Steve. At the Pleasant Grove Canal downstream, they had conical fish screens and they installed 2. And at this point, we're installing 1. And I wonder, was that selection there, was that a function of the amount of water that's going to be going into that canal? How was that arrived at?
Yeah, we looked at doing two because, yeah, realistically, the district could use a smaller screen at this point and meet that kind of 8 CFS target that they have. And then, we could have built that alcove to be wider, to have space for a second one to go in the future. But as we looked at the cost, I think each one of the smaller, so, just round numbers, but each one of those smaller screens maybe costs like $60,000, something like that. And the bigger screen cost $80,000. So it's just not that much more expensive to go to the bigger screen. And it really, it could save money in the long term. It provides, the district with a system that works now and gives them a lot of flexibility and not the need to go through the whole, process again in the future, and not open up this can of worms, I guess. So I think the district saw this as a good way to just go forward, make a little bit bigger investment at the beginning, but that will give them a lot of flexibility moving forward in the future.
Thanks, John.
I think, Tanya, did that kind of hit what you think?
It does. I mean,
Okay.
it does, John. I mean, there was a few other things that pushed us towards that decision with the double pipe, and
Yeah,
it's kind of sitting there and not being used, and
yeah,
um,
yeah.
it
To do
just
that
seems more
bigger,
prudent.
to do that option where we've got two bays where one sits silent for, I don't know, 10, 20 years. It seemed like maybe not the best use of resources right now. So that's how we got there. All right, we'll step on. This is just a quick section of what modifications in the canal would look like. There's a little bit more work to do on that to help folks know, but I think at the deepest, we're maybe lowering the canal. These dotted lines here, I think, are 1 foot. So it's like 1.5 feet or something that we're lowering the canal kind of at its deepest point. Just so folks have something in mind of how major that is. Then we get into structural sheets and structural details, which are really exciting to look at if you're a structural engineer. I'm not sure they are for the rest of us. But there is, I wanted to just kind of look at. So yeah, this is kind of these stop logs or dam boards as we call them here. So yeah, they'll have a guide slot, they'll slide up and down. They're made out of aluminum. They're gonna have this neoprene strip on the bottom. So the idea is you push them down and they kind of seal against each other. We'll have these aluminum rods sticking out the ends of them is kind of the pickup points. So we've got something that you can grab them with. And so one guy or someone grabs them on either side and pulls them up. But here's these board lengths. So it's on the two ends, it's nearly an 8-foot board, a 7-foot 9-inch board. So that gets to be a little hard to handle. And I think actually on some of these, I think they said we might have to go up to a 3-inch wide in order to have the hydrostatic pressure to handle it when the Auburn Ravine is running full and we've got dam boards in to be able to support the system. That's kind of what those look like. Let me look a little more details on the structural stuff here. We did go to in order to support these, I guess when we pushed out, at one point we had this whole structure a little smaller and we only had 1 foot of open space between the screen and the walls. I just really felt like that was going to be a little tight for maintenance, for getting in there and cleaning out sediment and stuff. So when we made that bigger, it ends up making kind of everything bigger. So our dam boards got bigger, and to hold the weight of the water when they're full, we ended up going to concrete piers out here. So this here and this here are 2 concrete piers. They both serve to hold up the catwalk and to hold the dam boards in place when we've got those in. So that's what those are out there. I think it just also offers some protection of the screen. So if, I don't know, big logs are coming down or something, that's a little bit higher protection for those screens. So there'll be walkways and handrails and all that good stuff around here. There will be a ladder right here to allow access down into this space for maintenance purposes. We'll
Before you
stay on
move
that
ahead,
one. Yep, Jim?
Jim, go ahead and unmute yourself.
Okay.
Maybe not.
Took,
Yep.
took a little while for that little button to come up on the screen. So if I'm understanding correctly, regarding the aluminum stop logs that would be put in there to prevent water from flowing to the screen, right? The typical use of that would really be during the non-irrigation season, when NID is
Correct.
going to say, well, we don't want to send water, through the screen down the canal because we don't have any customers that want any water, right?
Correct.
So I can see the benefits there of using the aluminum because it's lighter and because it's
Mhm.
only going to be, it ends up being about half a year sometimes where they would have
Right.
those in place. So it's
Yep.
still a substantial period of time. But that does tend to reduce the sedimentation problem around the cone screen because that's your high sediment time of year is the,
Yep.
fall and winter. It kind of makes sense from that point of view.
Yep. Yeah, it's kind of part of the thinking is just keeping the sediment, keeping the debris out. If these dam boards are in here, no matter how much neoprene or whatever we put in, if they're in there all non-irrigation season, you're going to have a pool of water in here
Yeah.
unless you get really excited about keeping it dry.
So
But
on
you
the
won't be collecting all the sediment and all the
Okay.
stuff.
So on the electrolysis thing, if the aluminum boards are sliding down into aluminum channels, you don't have electrolysis.
Okay.
If the aluminum boards are sliding down into concrete channels, you don't have electrolysis. But if the aluminum boards are sliding down into iron channels, then you're going to have electrolysis, and either the iron or the aluminum is going to get corroded quicker than you would think, and
Yeah.
you're going to have a type of fusing that goes on there sometimes when you have contact one on the other, or you're going to have it degraded to the point where it leaks a lot.
Yep.
So
Yeah, so
Very
there'll have
good.
to be some sort of insulator or, and I don't know if that's even what's indicated here in the detail. I noticed that there was some sort
Yeah.
of
So it has this UHMW strip each side. That's a ultra high molecular weight plastic, isn't it? Isn't that what that is?
I'm not familiar with that acronym, but
I
maybe
believe.
when you talk to your structural guy, he'll say, we
Yep.
thought of that. And that's what
Okay.
Yep,
it is.
exactly.
okay, thank you.
Yeah, it is. We kind of use this as a standard detail. As I mentioned before, we've used it a ton of times on a lot of dam projects is where we end up using them a lot. All right, going on. This is just,
John, we have another question from Chris Conway. Chris, please go
all
ahead.
right.
Hi, yes, I just want to comment on the UHMW. Yeah, it's commonly used, good material. You can put it in strips
Yep.
with embeds and concrete and have it so it can be removed for maintenance. Yeah, ultra high molecular weight polyethylene.
Polyethylene, there it is. Yep. Excellent. Thank you. It's always nice when I get on like a web meeting like this and I'm sharing stuff and I'm supposed to be like, presenting to you guys, and here you guys are teaching me. This is the way it should be. I love it. So yeah, these are just some sections of that facility. I guess, like I mentioned, we'll have a 3-foot diameter hole coming out here. One of the kind of in those mechanical sheets that'll get drawn up is there's going to be, Mike will end up doing a ductile iron. There'll be a little spool that will go into a short radius 90-degree bend that will go into a PVC 3-foot diameter pipe heading on out. So I think that's what that's going to all look like under here. It's going to be one of those fun things to build where you're going to have to put in the pipe and the elbow and the spool, and then you're going to have to form your concrete, and then you're going to get to pour your floor. So it'll be an interesting little construction project, but not super uncommon. Yeah, so here's just a kind of looking at that pier is what that piece is. It's sitting there, and these aluminum stop lugs in here. I think a couple things that are going to change in this, just that we've got that, we're showing it like right close to the edge. I want to make sure we've got that we're not getting too close to the edge, that when we put in the fasteners for this channel, we're not knocking off concrete. And then just also making sure we've got enough space between where you pull these stop logs up and where you run into your handrail, so that it's actually like maintenance folks can reach over there and actually do this without dropping all the stop logs out in the ravine. So we're working on that detail just a little bit more. This is this control box I talked about. So we'll come out of the cone screen and that 36-inch diameter pipe. That pipe will come into this control box here. Probably better look at this one. We'll come into this control box, and the water will have, well, we need the profile or the section. There we go, that'll work better. So the water will come in, and it'll end up building up to get out to the canal, probably doing, I can't remember exactly, but an elevation, something like that. And then it will flow out through this, this deal here. And what this is a one-piece slide gate and flow measurement device. So the water will kind of pool up in here. It'll exit out through this thing. Inside this, there's a bunch of transducers that measure the velocity and the depth of water that's flowing through this. And then the control system controls what this gate does. So if this water level goes down to here, then maybe the control gate opens more to be able to provide enough water. And if for whatever reason the water level goes way up here, you would have more hydrostatic pressure that would be pushing the water out, so the gate would close some automatically. So the operators kind of dial in and say, we want 5.3 CFS, and no matter what this water elevation does, the gate compensates for it. So that's kind of how that system, what that is and kind of how that works. Again, we anticipate this will be a place that, there's going to be probably some sediments that collect. I just really don't know how much, but if they do, we have an access panel and a ladder for the staff to be able to get down in there and take care of that sediment or whatever debris. Well, it wouldn't be debris other than sediment that we get through the fish screen. So whatever sediments collect there. And then as this goes on out, the canal ends up being kind of like this, that it goes on up to the canal. Something like that. Just to give you an idea of what that looks like as it flows on out. And I don't think there's much else on this. There'll be a handrail on there. There'll be a control system on there at some point. Yeah, and then this is just a little kind of a site plan we put together for PGE to show where that power would come in and how, where it would get across. We'll have a few more detail sheets that'll show up behind this that'll, talk about what that trench looks like, what that crossing looks like, what this what the service panel looks like here at the cone screen. So that's another piece that'll be coming. So I think that's kind of, there we go. We made it through 35 sheets in an hour. Are there any, I guess, looks like Steve's got a question, I see.
Yeah, I was going to bring up, were you aware that there was a sewer pipe crossing installed just about at the same place a few years ago? And are you coordinating with that in terms of placement of your underground electric and the other work you're doing?
From everything that I can tell, that sewer pipe is right up here. There's an easement that's crossing it kind of further upstream.
Yeah, that's our understanding.
Yep.
Thanks.
Yeah, so that should be well out of our out of what we're messing with. And so yeah, certainly before the contractor does any digging out here, he'll do all the locate services stuff and just make sure. But yeah, to the best of our knowledge, there's nothing else right here in this work zone that we're working in.
All right. Jim,
Looks like
you
maybe
can go
Jim's
ahead.
got another question.
Yep. Oops. I might have double clicked you there, sorry.
Uh, Okay, now it's working. Okay, you can hear me now? Okay, good.
Sorry.
All right, okay.
Yeah, we got you.
So where was I? Upstream of the new facility, there was some mention of, in previous design discussions, some mention of bank stabilization upstream from the new construction.
Yeah, so we've determined that we don't need any additional bank stabilization up there at this point. I really believe that in the just this whole natural system we're putting in, getting rid of those dam boards that were used to stop up the water here across Auburn Ravine is going to get rid of this cyclic raising water and dropping water and raising water and dropping water. So I think it's really it'd be best to just watch this and see how the system responds to this. The hope is that vegetation is able to kind of creep back down the banks a bit more and reestablish in these areas. So yeah, we really just felt, I think, unless Tanya, if you've got something else you want to say to that, I think we just kind of decided that that was something that didn't need to be dealt with as part of this project.
That pretty much sums it up. It just generally though, around the actual construction zone, there will be some bank stabilization there. But anything further upstream, yeah, we determined it wasn't needed.
Thank you.
Okay. Jack Sanchez, please unmute yourself. You can go ahead and speak. Sorry, Jack, I guess I'm having some, can you speak now? I'm gonna press the button one more time. Hopefully it'll work.
Oh,
There we are.
I'm unmuted
All right.
now. Tony.
Thank you.
Okay, this is Robert Hain, and he has a couple of questions. Thank you.
Yep,
Hi,
good
Robert.
morning. Got in the, yes, good morning. Got into the meeting a little bit late. You might have already covered this, but I do have just a couple of questions. Going to your roughened rock ramp that you're going to build, if I'm saying that right, is there a low point where it would not be functional at a CFM of like 37 cubic feet per second? Would it still be functional?
Yeah, so it's designed to, I guess maybe I should jump back. There we are. So when we design this thing, it needs to be able to function at 13 CFS is kind of the 95% exceedance, which means that 95% of the time there's more than 13 CFS in there, and up to at least 172 CFS. So that's kind of the low point. Once there's less than 13 CFS flowing down that roughened channel, it'll still, I mean, water will still flow down it, but it won't have the foot depth that's needed. And really so that 13 CFS here that number was built collecting numbers from both the gauging station downstream and also the NID canal, putting them together. So if you subtracted 6 out of that, you get like 7 CFS. So actually in that triangular channel, in the low flow channel, 7 CFS is kind of what fills up that low flow channel.
Okay. All right, thank you. One other question, in regards to 100-year storm, what is the high point that this still will be functional after the storm? Has there been any statistics on that?
There's a high point. So this 100-year storm this is the water surface elevation up here, if you can see that screen. That's got like 15,000 CFS or something like that. So at that point, there's just water everywhere. If you ever get 15,000 CFS down Auburn Ravine, it'll just, everybody's going to be wet. And so fish, everything's going to be everywhere. So then as the water starts coming down, I guess where it, I'm not sure how to answer where it functions again, but where the water will be confined back in the channel will be at about like 4,000 to 5,000 CFS is kind of when you get bank full flow that's going through there. And so, you know, at that, the roughened channel just kind of, I guess it works at any flow rate in that range, just with water flowing over it, I guess. I don't know, is that answering your question or am I missing it?
Well, no, I understand if you got 15,000 cubic feet per second coming down Auburn Ravine, that's a tremendous amount of water. We just had a winter here, if you want to call it a winter so far, where we had water going over the top of the gauging station. And I think, if I'm not mistaken, that's 1,000 cubic feet per second to fill up that compartment, if you want to call it that. So at 15,000, you're looking at 14 times the water that we just had. So my next question, I still want to incorporate this into my question. And I'm sort of leaning to the gauging station as it is right now. It's been in there for 10 years. It's still functional and it works with concrete weirs. And so I'm sort of an advocate of the concrete weirs so that NID doesn't have to come back in and rebuild this rock and ramp. So that's basically my question. If, you know, your question really didn't answer, or I should say your answer didn't answer my question, because at 14,000 cubic feet per second or whatever that is, without the weirs, I don't see how it's going to be functional for fish passage. And so that's a concern of mine and SARS's. So, if you can sort of answer that for me.
Yep. So the rocks that go in there, I'll jump onto that. We got that profile. Oh, right there it went. So the rocks that go in here that form up this roughened channel are sized for all of those flow rates. So in our modeling, we go through from, you know, the low flow of that 13 or 7, whatever, all the way up to 15,000 CFS. And we look at where do we see the highest velocities and the highest shear stresses on these rocks. And that's what we designed to. Then we size the rocks appropriately to be able to withstand the velocity and the shear stress that is experienced at those flow rates. And so what we found is at the 15,000, where you have water everywhere, the velocities and the shear stresses are actually lower because the water is everywhere. There's more pressure that's pushing down. There's all sorts of different forces going on. The worst case scenario is really more in that 4,000 to 5,000 CFS, where you've got bank full flow and it's just ripping down through there. And so that's what the rocks are designed for, that we put in, is to withstand those flows. There will be some of the smaller rocks are going to move. That's just the nature of how a natural system works. But those big rocks are stable at that flow rate.
Okay, thank you.
Yep.
All right, Steve, go ahead and unmute yourself.
Yeah. Hi, John. I got a question. At the other end of that flow velocity, where we're talking about that 13 CFS through that channel, will this structure be capable of allowing salmon to navigate it with water velocities of 13 CFS?
So the 13 CFS is not a velocity, that's a volumetric flow rate. So when it's flowing at 13 CFS, so when it's at like 7 CFS, so it's low point, the water surface elevation is going to be something like that in that little channel. And we'll get a foot of depth, which is what we need to have for, you know, to meet the criteria for passage. And the velocities in that channel, because it's this roughened rock, the velocities are about, 3 to 3.5 feet per second. And so they fall under, I think the criteria is 4 feet per second, I believe. So yeah, it does. So salmon will be able to swim up that just fine. in that roughened rock state. And so, there'll be some spots obviously where it'll be faster, and then there'll be some spots where there's a little eddy where the fish can rest or where it's slower. So it'll be a varied system, but looking on the whole, it functions and will allow passage at the low flows.
Was there any thought given to, you mentioned eddies and resting points for the fish. Was there any thought given to constructing that type of a low spots in that channel so that there were, artificially created places where salmon could stop and rest as they migrate up it?
Yeah, I mean, we could. There's a lot of ways to skin a cat, right?
Yeah.
So there's a number of ways that this could have been built. This could have been built with the concrete weirs that Ron mentioned. It could have been built with boulder weirs and pools. It could have been built with, a vertical fish ladder. There's, a lot of different ways it could have been done. But this is the way that we chose to do it.
Thanks.
And
Yeah.
to John, with the different gradations of the rocks, adding those larger rocks, will give kind of some of those natural resting spots for fish too. So even though it's not the typical of what you see with the chutes and pools, there is some of that in here with those larger rocks, right?
Yeah. Yep, that's how it'll work.
Okay.
Any other
Is there any
questions
other
or
questions?
things you want to talk through?
Got a couple more here. Tim, go ahead, unmute yourself.
You got me.
Yeah, I'm thinking you'll probably be putting out a summary of the meeting. Will that include a list of attendees?
Yes.
Thank you.
And then Director Peters, do you want to go ahead and unmute yourself?
Yes, good morning. Thank you for this. This is really informative. I'm kind of late to this. Is the first one of these design meetings I've attended, but I'm curious, and I'm sure it's already been answered before, but are there other installations that I can look at that have this rough and rock ramp that I can look, where else are these done?
Yes, there are. And I don't know off the top of my head that I can throw out a bunch. I know that we've done, dang, where did that one go? I think it was up in Idaho. I'd have to look it up and see where it went. And I know that that's one other one that McMillan Jacobs has done that I know for sure. But I know that these have been they've been used for a number of years. They don't have like a real long history of the science behind them and how they work, but just this concept of trying to create more of a natural stream setting, has been around for a long time. But yeah, there's a number of different places, and I can look those up and send you some links to some of those if you'd like.
Yeah, and just to find a track record of how they have performed, the ones that have been installed over time, how they have performed. That would be fantastic. Thank you.
Yeah. And then go to unmute maybe.
If you're unmuted, unmute.
Somebody's unmuted. Okay. Steve, you want to go ahead?
Sure. Hey, for you, Tanya, I've got some procedural questions. When are we going to publish an RFP? When do we think we're going to circulate that? What do we think the award criteria is going to be? And issues like pre-bid meetings, can you kind of run down that scheduling for us?
Yes, we actually have completed a pre-qualification for contractors, and that list should be available on our website now. From that group of pre-qualified contractors, we will be asking them to bid on the project. We're hoping to have the bid package completed by the end of the month. And the bid period there will probably be about a month. So we're hoping to award in May and give authorization for a notice to proceed soon thereafter, so so that the contractor can be prepared to start construction during the in-water work window, which we anticipate to be mid-June through mid-October. And that in-water work window is important for completion of the rough and ramp, completion of the concrete alcove. The other work, the actual installation of the cone screen, regrading of the canal, and the control box, the gate, that'll occur during non-irrigation season, so after October 15th.
Great. So, question, are you going to make the RFP available on your website? And then two, do you think you're going to have a pre-bid meeting?
So for the RFP being available, that might be a little sticky for us because we're only inviting a group of contractors. We certainly can have the final design and final technical specs on the website, but not necessarily the notification to submit for a bid. I'll have to talk to Doug a little bit more about that. For the pre-bid meeting, typically we do that with these type of projects because they'll have a multitude of special conditions. So we definitely like to have the contractor attend a pre-bid meeting.
Thanks, Tanya.
You're welcome. Okay, I have a couple more questions here. Director Peters, you can go ahead and unmute yourself.
Okay, thanks. I was just curious, maybe you covered this at the beginning of the meeting, but what's the status of permits?
Status of permits. So we have a couple steps we're doing parallel right now. NID is not a participating entity in the PCCP, but we are trying to gain coverage under that. So we're doing a couple things. We're developing an agreement with the PCCP to allow us to participate. And then we're developing the draft permit. So a permit for the PCCP, as well as draft permits for the 1602, which is also known as a stream bed alteration agreement, and then our water quality permit. So those are all currently under development. We've been meeting with the agencies to gather their comments, make sure that we have all the information that they need. Everybody's very supportive of us participating in the PCCP. So we do think that that's going to go through with no problems. We expect to have something actually before the board, NID board, to get authorization to go ahead and enter into an agreement. Our target date is this upcoming March 23rd meeting. And with that, then the PCCP will bring it before their board, which they have scheduled March 30th. And so during that time, we hope to submit our draft permit packages to all the agencies for the review.
That's great. That's great. And so we anticipate to have all of the permits by the time construction starts, or it doesn't sound like it's going to be by the time they're bid. But...
Okay.
It may not be by the time we bid, but certainly by the time we start construction. Yes.
Absolutely. Sure, sure. Thank you. That's great. Good job.
You're welcome. Thanks. Jack, you can go ahead and unmute yourself.
Okay, thank you. John Berge, I have a couple of questions for you. Would you be willing to send me your email and your direct line phone number in case we have additional questions that we could ask? Because these meetings are so rarely scheduled. And secondly, on the right side of Auburn Ravine below the dam, right side looking downstream, is a mixed oak woodland rainforest that's just absolutely pristine. Are you certain that we're not putting any barrier on that side of the Auburn Ravine will preclude flooding and damaging that mixed oak woodland during a 100-year storm? I'm just wondering.
You are, I'm trying to get to a picture where I can see, I guess maybe this is the best one. You're saying kind of down over this way? You see my screen?
Yeah, if you stand on the dam where it is right now, on the right-hand side, looking downstream. Yeah,
Yep,
as you come in from the road there, yeah.
yeah, so kind of right in that area.
Yeah, yeah.
So what I can, for the 100-year storm, it's, I mean, it's all going to be the same as it was before. That's part of that, kind of that no rise, that things aren't going to change there. So really the bigger concern for that, I think, is what happens at this 4,000 or 5,000 CFS storm. But really, I don't, yeah, it's by the time you get down there, you know, the whole point of a roughened rock channel is to dissipate energy. And so before, what we had is the water would flow over that structure, it would hit these rocks and the, you know, the grouted riprap in the pool there, and it would dissipate energy there and then flow out. Here, we're going to be carrying that energy farther down, and we're going to be spreading that energy out across all of this. But by the time it gets to the bottom, it will have lost that energy. And so I don't know exactly where those trees are that you're talking about, but I don't see anything that we're doing that is going to cause any erosion on this bank down here. If that's, yeah.
I'm not just talking about erosion. If you look at your diagram where it says Auburn Ravine,
yep,
that area with all those beautiful oak trees in there is
okay,
the area that I'm focused on. And
yeah, so
do you
our
think
project's
that
not
without a
gonna
barrier?
have, our project won't have any effect on any of that. Yeah,
And you're
nothing we're doing
certain?
is gonna change that.
Okay, great, thank you.
Yeah.
Okay. Any additional questions about the plan set? Was there any questions about the technical specs? I mean, in general, they're pretty typical. Is there anything special you wanted to point out, John?
The only thing, if anybody wanted to look at them, is we could quickly review. I think the most interesting thing in there is this ESM, that engineered streambed material. If anybody wants, if you want me to kind of walk you through what that material looks like and how it's different than riprap, we can do that.
Yeah, why don't we go ahead and pull that up?
Okay, give me, I don't think I had that pulled up, so give me just a second to get there. And we will have fun looking at technical specifications. John says, laughing. Okay, so in the technical specifications, if you guys do get to that and need something to put you to sleep, there's all these different areas. And so the ESM, this engineered streambed material, lives in the earthwork section. So the 3100 section is earthwork. And so what we've done, this is, a lot of this is standard language of how contractors deal with all sorts of different earthwork. So anything from topsoil to riprap to sand to gravels. And so we've created this ESM material and said that this is the material that we're going to put in there. And it's really based off of CDFW guidelines on creating this engineered streambed material. So the this kind of defines a little bit of what that material looks like, what it can and what it can't be, how its dimensions work. And then here is where we define by rock class A through H, the size of these rocks. And so this is where the size A, B rocks are these, 1.5 to 2 foot diameter rocks. So you can see that 8% of them will be these bigger ones, 7% will be a little bit smaller, 7% a little bit smaller. The other thing here is there's this installation method. Installation method A means that they're hand placed. So all of these rocks, these ABCs get hand placed. D and E, you'll see are the same size rock. And so kind of the intention here is like half of those rocks get hand placed and the other half are part of this kind of from 18 inches down to down to 2 millimeters is material that will get probably placed out of an excavator bucket or wheelbarrows or somehow that the contractor is going to get that material out. And that's the material there. This F through H is the material that will get kind of set into its final place using these flooding and jetting methods that will do that. And so that's where you see kind of the percent by volume of how many of these different rocks we've got in there, and then kind of the percent that's passing of each of those. And what we shoot for is, we talked about that stable rock at those high velocities. Well, that stable rock is like 1.5 foot diameter. And so that's where you get this 18-inch, and at least 50% of the rocks are going to be bigger than that, and 50% will be smaller. And so it's these smaller rocks and sand, gravels and sands are what are going to be moving around at those high flow events. The bigger rocks will be stable. And so that's kind of where we see the movement of what that looks like there. And the gradation. And this is, and kind of to note, this is different than like a riprap gradation. So if you had a riprap that was a size D50 and it was graded, it would look a lot different to this. Nobody wants all of these fines in their riprap. That just doesn't. So if you size riprap to like a D50 of 2 foot, you definitely don't want a bunch of 2-inch material in there. That defeats the purpose of riprap. So it's important for us as designers, for NID as the owner, and for the contractor to all understand that this is a whole different sort of this is a whole different thing than just dumping riprap or placing gravel. It's not similar to either. So I think that's probably the only thing that's really very interesting in here, unless someone else has something else that they want to look at or learn about. Looks like maybe Jim's hand is up. I see.
Yeah, Jim, you want to unmute yourself?
Yep. So I noticed somewhere that the thickness from top of the roughened rock ramp down to the bottom of the roughened rock ramp, I'm not talking like longitudinally along the creek, but I'm thinking just the depth of the ramp structure itself is about 3 3/4 or 4 feet of material, right?
Right.
And of course, we know that the existing pool below the existing Hemphill Dam is pretty doggone deep.
Yep.
So there's going to have to be a whole bunch of stuff filled in there up to the point where you can begin to place these rocks we're talking about here to create the ramp.
Right.
So how,
I probably went too far back.
how are you
One
going
of
to
those
handle
cross
that?
sections
Yeah.
showed that, or showed at least part of that. I'm not sure if it was cut through the worst scenario, but like that one shows, this
there you
area
go.
in here will have to be filled.
Right.
And so I do, in kind of our next, what we're working on moving forward is defining what that fill material is. And, to a certain degree, it doesn't matter a whole lot, but it matters that it's put in and it's compacted and it's solid.
Right.
And then we build off of that. So yeah, there will be fill material in there. I think on maybe this last, there I saw some more, there's some more fill material. So all of those areas, you're right, Jim, are going to need to be filled and compacted before we can start bringing in and building up this final, or these 4 lifts, I guess, of 3.75 feet of material.
Okay, thank you.
Yep. Yeah, and I think that's all I've got.
Okay, yeah. Is there any additional questions? Well, thank you everybody for coming. If something in terms of questions, comments come up in between now and our next kind of revision set, I would ask that you do submit them to me by March 18th. That way we have adequate time to review and address them. You can email me or you can call me. My contact information is available if you don't already have it on our website. Jim, go ahead and unmute yourself.
Yeah, I just want to let you all know that I do file regular reports with the salmon regarding your progress, and they're all very happy about this. So thank you for your good work.
Awesome. Thank you. Okay, great. Well, thank you again, everybody, and we'll see you next time.
Thank you.